Okay, let's make a start. In the last lecture, we went through the derivations for the telegrapher's equations, okay, and then we were able to derive, like characteristics of transmission line, like Z0 and delay, okay. Now we're going to look at developing a two-port model for a transmission line, okay. And first of all, we're going to do that in the Laplace domain, okay. So we have all these different domains. We have remember last year we had the time domain, the Laplace domain, and the frequency domain, okay. So in time domain we should be able to do everything, includes nonlinear systems, okay. Laplace domain we can do transient and steady state as well, but it means that it's linear, okay. The system has to be linear, okay. And frequency domain, it also has to be linear, but it's more restricted. It's only sinusoidal steady state analysis, okay. And you can't mix these, okay. And remember, when you talk of impedance, it only has sense in the Laplace domain and frequency domain, okay, because you have a resistance in the time domain, but you don't really have an impedance, okay. So keep that in mind. Okay, so in the Laplace domain, we can look at our model for a small section of transmission line again. Okay, so we've got our little bit of delta x of transmission line, and we can write down using KVL and KCL. We can get these second order partial differential equations, okay, using the time domain representations for the components, okay. And then we could transform time domain to the Laplace domain, knowing how derivatives transform in the Laplace domain, okay. And then that would get, assuming a discharge line. That's one thing we also we assume initial state of 0, okay. The other way, and then we get a second order DEs in x and s, okay. And then these are not partial DEs anymore; they're normal differential equations, because effectively we've absorbed the time derivative into the Laplace domain. So that's what we use in the Laplace domain. We use that in circuit analysis basically to get rid of the time derivative, right? Okay, so we can turn differential equations into algebraic ones, and that's what we've done here. We could also do it directly in the Laplace domain. So, and I'll go through that now, just as a bit of an exercise, okay, just so that you can see where everything comes from. Okay, so we can go. We've got our little bit of circuit. Okay, it looks like it is L delta x. And we've got some resistance R delta x, and then we have some conductance G delta x, and we have C delta x, okay, and then we've got, and we put this in the Laplace domain, so it would be V x plus delta x s, okay, and again we can put this in the Laplace domain, so the impedance would be S Lx, and this would be, right, and the actual impedance here would be 1 and SC, but the conductance would be, if we looked at it as a conductance, would be SC, okay, we'll see later why we do that, okay, and then we have Vx of s here, and we have Ix of s coming in, and Ix plus delta x of s going out. Okay, so we could do KVL around that loop. So we can do two things. We do like we did last time. We did a KVL around here, and we do KCL here to get the two equations. One giving us an equation in V, and another one giving us an equation in I. Okay, so we could say this is delta VL. Okay, and this is delta VR. Okay, and so going around that loop, we'd have delta VL plus delta VR. Plus Vx plus delta x of s minus Vx of s has to equal 0, okay? And then, that would be on this side, just rearranging things and filling some stuff in, minus Vx of s equals minus, it's going to be delta x minus delta x outside of SL plus R, right? Okay, times Ix of s, okay, because these are the impedances in the Laplace domain, okay. And then of course it's a limit as delta x tends to 0 of Vx plus delta x s minus Vx of s on delta x equals minus SL plus R Ix of s, okay, which is going to be d dx equals minus SL plus R Ix of s, okay. So that's called equation 1, okay. Right, yeah, okay. And then we could also do KCL, okay. So we could do KCL at this point. Okay? Remember we did KVL, and last time we did KCL. Okay, and then we could say, we know that since this is a lump model, okay, we know that this Ix of s here is also Ix of s there, okay, and we've got delta Ig, and perhaps we've got delta Ic, okay, and then we have this Ix plus delta xs going out, okay. So we can see that, writing that down, we've got Ix plus delta x of s, okay, equals Ix of s minus delta IG plus delta IC, okay, and this delta IG is going to be, and then we rearrange that and bring that over here, Ix plus delta XS minus Ix of S, okay, equals minus delta X, and delta IG is going to be basically G delta X times the V, okay, because it's, it's divided by R, but it's times by G because G is 1 and R, right, so that's why we have the G there, okay, G, okay, and then for this one, going to be SC times V, okay, that's going to be the current, okay, because, normally this is the impedance is 1 on SC, so the current going through that element is the V divided by the impedance, okay, so it's got to be SC, so then we've got plus SC, V X plus delta X, comma S, okay, and then again we take the limit tends to 0 and we end up with, EIX S dx equals minus SC plus G outside of Vx of S, right? Okay, so that's 2, okay, so we can say we take the derivative of first one with respect to x, okay, so we go, 1a is, we'll actually move that under here like we did before, okay, just by skipping steps because we've done it a fair few times, okay, so and then this becomes the derivative, right, okay, so so take the derivative of, again on both sides for equation 1 we get SR plus R dIX S dx, right, okay, and then for that 1a, and then if we put this into there, okay, then we've got dx squared equals, it's going to be minus, which is plus SL plus R SC plus G Vx S, okay, so that's same form as what we had before, like a second order, it's a second order differential equation, okay, relating, the V to V, the second order derivative of V to V itself, okay, so, and you do the same with I, okay, just a few more manipulation, okay, so, and then, and we end up with this, and we call this term here, gamma squared of S, right, okay, okie dokie, is that reasonably unclear or not? I did correct that, good. Okay, so we can do that, okay, so, and again, we know how to find solutions to those. So this is just a simple second order, it's not partial derivatives anymore, it's just a normal differential equation, okay, from one variable. Of course, as I said before, we managed to absorb the time derivative remove the time derivative by using the Laplace domain. So we know that a form of solution, we could try Vx of S equals, let's say V plus e to the minus Q x, right, okay, plus V minus e to the positive Qx, okay, so if we could try solutions like that, okay, and so if we take the derivative of that, we get the Vx S dx is going to be, V plus, and it's going to be minus Q there, e to the minus Qx, plus V Q times V minus e to the Qx, okay, and if we go do it again, okay, it's going to be basically Q squared outside of V plus e to the minus Qx plus V minus e to the Qx, right, okay, is that clear? Which is going to equal Q squared times Vx of S, right, okay, so, providing that Q squared equals this gamma squared, this form of Vx of S is a solution, okay, 0 is also probably a solution, that's a trivial solution, we're just interested in non-trivial solutions most of the time, but, that's a solution to that differential equation, okay, sorry. Well, so we've got the model, okay, so we're trying to make a Laplace domain model for the transmission line, okay, and in fact we're going to make a two-port model, okay, so we're getting all the equations set up. So we did something very similar in the time domain, but then we had partial differential equations, right? Because we have the time derivative. But if we move to Laplace domain, we can absorb that time derivative or get rid of it with the variable S, right? Okay. So anyway, we'll move on, but you'll see that things will happen. Okay. So we got again we get solutions for I and V of this form. Okay. So obviously relating to waves travelling forward and backward directions. Okay, on the transmission line. And again, I'm not going to go through it, but like in the time domain, you can show that the ratios of this V plus and I plus is related by Z naught, where Z naught's given by this. Okay, and the ratio of V minus to I minus given by minus Z naught. Okay, so we talked about that in the last lecture. Okay, so we've got the forms the forms of the solution. Okay, so it's v plus the forward going away is e plus e to the minus gamma s x, right? Yeah, and we've got v minus e to the positive gamma s x. Okay, and we've got I plus e to the minus gamma s x plus I minus e to the gamma s x. Okay, so we know the form of the solution. Okay, but we want to eventually. We need to sort of find also these constants v plus and I plus and v minus and I minus, right? So they're things that have to be solved. And so you might remember some people here did 3021. Who did 3021 last year? You did. Remember, we had differential equations in the time domain, I think, for the RLC circuit stuff, right? And then we use initial conditions to find unknowns. Okay, so we had the characteristic equation, all that, and we use initial conditions in the time. Here we can use initial conditions, well, boundary conditions in the spatial domain. Okay, so that's how we're going to solve eventually for these unknowns. Okay, we have VI relationships at the end of the line as well. Okay, so that will eventually give us, and you'll see more of that as well in EMT, that you'll have differential equations describing fields, and you use boundary conditions to solve for them. Yeah, go on.
You mentioned zero state.
As for initial zero state, it's a good question. It's discharge line.
Does that mean zero?
There's no voltage on it. So I'm not sure. I have to think about it. I mean, I'm not. It's a good question, right? Okay, and I think that's there just to cover and to be correct. Okay, I'm not sure how well the model handles an initial condition. Okay, to be honest, because I have my doubts about the linearity when it's got initial conditions, right? Because maybe you could handle it by having these capacitors and inductors would also have voltage or current sources with them, and you could derive that. I'm not sure. Okay, but so if you cast back to last year when we transformed this into the Laplace domain, it wasn't just an inductor. It was an inductor plus a source, or a capacitor plus a independent source, right? Which represented the initial conditions. So I just don't know, to be honest.
So this is
no, it can be any. We're going to use it. Okay, this is a model of a section of line. Okay, and it's telling us something about the actual voltage, the transverse voltage. Okay, that could be propagating along the line. Okay.
And use stable equation 4 to use the Y.
Yeah, well, we're going to show you how. Yeah, I think so. This is an important concept. So we've been through and done this in the time domain, right? And so there'll be. So you've got to realise that there's waves that are travelling in the forward and back direction, right? Okay, and that together they make up V and I, and they have some relationship between the voltages and the currents. Okay, so even when we'll eventually do time domain analysis of transmission lines, and you have to keep those concepts in mind, because that's how you're going to solve. Okay, you'll see here we're going to make a two-port model for this transmission line, and it's based on. I'll go through how we do it. It's based on knowing that this is how the currents and voltages are, and that there is these backwards and forward waves. Okay, sorry, it's going to be a transmission. Yeah, transmission parameters, right? Okay, you'll see in a minute. Okay, a few minutes. Okay, so we need to get something that relates the VIs here. And so we want to make a two-port model for our transmission line, right? We're going to say we've got a model transmission line of length L. Okay. We need to make a two-port model. So a two-port model is just going to be a 2x2 matrix, right? That's going to relate the I's and V, the V and I here to the V and I there. Okay. That's what a two-port model does. Okay. So let's do that now. Okay. So we've got our bit of transmission. We say here it's x equals 0, and say here x equals some length L. Right. Okay. So at the input we've got I of S. We'll call it I1 of S. That's the port 1, and we've got V1 of S. Right. Okay. And at the output, remember we always defined I2 as going in, and we got V2 of S. But remember in our model for the transmission line, we always had current going to the right. Okay. So really we're interested in minus I2 of S. That's our that's what we're really interested in, because that's going to correspond more to our model. Okay. Okay. So so we know that V1 of S, okay, is equal to V naught, okay, V at x equals 0 of S, right? Okay, because we've got V of x, S here is given by this, right? Okay, is that clear? That at the beginning, x is 0, right? So then that's just going to be equal to V plus V minus, okay? And that would equal Z naught of S times I plus minus Z naught of S, I minus, okay? Because the relationship between the forward Z naught with the forward and backward waves, okay? As remember we said, we talked about last time. And we also know I1 of S equals I naught S, okay? And that's just going to be I plus I minus, right? Okay. So, we could put that in matrix form, right? So we're going to put that in a matrix form. Okay, so we're going to go V1 of S, I1 of S. Okay, and we could put it in a form that looks something like this. Z0 of S, 0, 0, 1, and this goes 1, minus 1, 1, 1. Okay, and we've got I plus and I minus. Okay, we'll call that 1. Okay, so if we multiply that out, let's have a look. Z0 times 1. Okay, it's going to go there, and that's going to be I plus. It's going to work out okay. And we're going to have Z0 times minus 1, and then it'll be I1. That's I minus here. And then this one is, on this second row, is going to be 1 times I plus and 1 times I minus. Okay, so that's put those equations into some matrix, right? Okay. So now let's look at x equals L. Okay, so we know that V2 of S, that it's the total voltage at that terminal. Okay, that's going to be V at L comma S, right? Okay, so it's going to equal V plus e to the minus gamma S L plus V minus e to the gamma S L, and again that's going to equal Z0 of S times I plus e to the minus gamma SL minus Z0 of S e to the gamma SL, right? Okay. So, and then that's 1. Okay, so we've got minus I2S, okay, is equal to I of L of S, okay, and that's going to be equal to I plus e to the minus gamma SL plus I minus here, e to the gamma SL, okay, and again, we could put that in matrix form, okay, we can put that in matrix form, and it comes out to be V2 of S minus I2 of S equals, again, we have this same matrix here, but now we have these coefficients here, which we've got to put in, e to the minus gamma SL, that's going to be minus e to the gamma SL, and this is going to be e to the minus gamma SL, and this is going to be e to the gamma SL, right? And it's going to be I plus and I minus. Okay, call that equation 2. Okay, is that clear to everyone? Go on. You could. You could, right? But you'll see why we don't, okay? But you could, absolutely, okay? It'd be just a normal 2x2. So what could we do now? What does a two-port description, transmission matrix description of a circuit element give? It gives do we have it here? You get this. I was trying to. Oh no, I think it was in the other ones. Does it have 2 ports? No, it doesn't. But it's just a 2x2 matrix that relates V1I1 to V2I2, right? Okay, that's what it is. And here, if we could find the inverse of this, okay, so if we've got I plus and I minus in terms of V1 and I1, then we could just put that there, okay, and then multiply out that matrix, those matrices, and we'd have a 2x2 matrix which relates V2I2 to V1I1. Okay, so that's what we'll do. Okay, so we need to get the inverse of this. Okay, so we can do that. So we're going to invert those two matrices, and it comes out to be, you get I plus I minus. Okay, and first of all we need to do this one. Okay, and we know the inverse for a diagonal matrix it's just the inverse of the diagonal elements. Okay, so it's going to be 1 on Z0 of S, 0, 0, and it's going to be 1. Okay, and this is going to be V1 of S, I1 of S. Okay, and then this one, it's for 2x2. For these, it's going to be the determinant. Okay, and then you just have to switch around these diagonal elements. So it's going to be +1 and -1. Okay, so that's going to be the i's expressed in terms of the V1 I1. Okay, and then we can put that together. So if we put this, so basically if we just tack that on to the end of that, okay, then we get V2 S, I minus I2 of S. Okay, it's going to be Z0 of S 0, 0, 1 e to the minus gamma SL minus e to the gamma SL e to the SL. Okay, times a half. We'll probably take that out the front because it's just a common factor, and then it's 1 minus 1 1 1 1 on Z0 of S 0, 0, 1. Okay, V1 of S I1 of S. Okay, so and if you multiply all this stuff out, you're just going to get a 2x2 matrix, right? Okay, and that's what you do. Okay, and you can use Euler's formula as well to get cos cos H and sin H, and what you get is this. Okay, you get that. Okay, that's our 2-port transmission matrix model for a transmission line of length L, right? So and that's what PSpice and all that can use to model transmission lines when you do simulation. So that's how it was obtained. So so that's how we've gone from using circuit theory itself and looking at infinitely small section of a transmission line to eventually ending up with a two-port model, valid in circuit theory, which is relating the V's and I's at one side of the transmission line to V's and I's at the other side, and of a finite length L of transmission line. Okay, is that clear? So you don't have to remember. I wouldn't ask you to derive that in an exam, of course. Maybe in an exam or a quiz you might have to write down some of these equations, or do KBL and KCL to do some part of this. Okay, but you don't have to remember this. In fact, you get a formula sheet which actually gives the actual model for it. Okay, so don't remember everything, but at least you know how it came about. Okay, so this is how we've derived that model. So, is any questions on that bombshell? Anyone? Okay, where are we? Yeah. Okay. So at least you understand. I think if you go through the math, I could just wave my hands and say go look at some textbook, but I prefer to go through it. So at least you know how it was obtained and how it's come about. You probably appreciate it a little bit more. Okay. Okay. So we just finished that. So next time we'll look at getting a model in the frequency domain, okay, and we'll look at a different route of getting a model. So you probably could in the frequency domain, with some careful caveats and being careful about how you do it, employ this model in the frequency domain with S equals J omega. But then you have to be a bit careful how you apply it and what you apply it to, and think carefully about how you're using it. But we can also look at trying to obtain a model in the frequency domain in a different way. Okay, so remember in the frequency domain we're looking at just steady state solutions to sinusoidal excitations. Okay, so remember that we're just interested in when we eventually get Vx of t, we're not interested in really this e to j omega. In the end, we're interested into the real part of this phasor representations times e to the j omega t. Okay, so we can go through now looking in the phasor domain. Okay, and we can get something similar. Okay, we get basically what you saw for Laplace domain, but now these forward and backward waves in the phasor domain. Okay, where the s is j omega in some sense. Okay. So now when we go into this is just telling us what the form of the solutions for v and I on the line are. Okay, so again in the frequency domain we again have these positive forward and backward waves. Okay, as well. Okay, and again we have this these relationships with distance e to the minus gamma omega instead of e to the minus gamma s. So and the approach that we're going to use. So if this impedance, so we've got an ideal source here. Okay, and if this impedance here ZS is linear, what can we say about this network looking in from the load backwards? It is. Everything will be linear, right? Okay. And if everything looking back in there is linear, what should we be able to find as an equivalent of that? Thevenin equivalent, exactly. So that's what we'll do. Okay. So what we'll do in the next lecture is, we'll actually find the Thevenin equivalent of that piece of line and the source and the source which has a ideal source plus an impedance. Okay. We'll find that, and then that equivalent model we can put and use. We'll have equivalent impedance and equivalent source, ideal source. And that's what we can use to solve circuit. Okay, so instead of using a two-port description, we use some equivalent impedance and equivalent voltage source. So that's another way to actually start solving problems with transmission lines. But now only in the frequency domain. Okay, so we'll stop there. Any questions? Anyone? Okay, thanks.